All right, in this lesson, we are looking at motion and sound. So we're looking at effects that are observed when sources of sound are moving. So we're going to look at the Doppler effect, and we're going to look at supersonic flight and sonic booms. So kind of interesting things. If you have no motion, you have sound, we just need to be able to visualize what that would sort of look like in the sound waves going out. And so this little applet here, if the plane's just sitting on a runway, you have sound waves just going out in circular patterns, right? Just going out in all directions. So that's what we want you to think of. And so you might have a certain frequency of the sound, 2,000 hertz or 20,000, whatever it is, doesn't matter, 10,000 hertz or something, okay? You have sound going out. So this little video here is kind of cute. I'll show it. Doppler effect ripples. Yeah, Doppler effect ripples. Doppler effect ripples in water. So it's just a funny little physics video that two brothers decided to make, I guess, while they're on vacation somewhere.
Hi, I'm Doppler Chai. Today we'll be demonstrating my effect called the Doppler effect. So let's look. This is a swimming pool, and notice the little kid down there. He will be our wave source for today. Okay, now I ask him to jump on the spot. Notice that the waves formed are equal distances apart.
So basically saying you have the equal waves going out equally all around. That's much like the applet I showed, the plane on the runway. And then,
so hence, each wave is generated at a constant frequency. Now I ask him to jump towards the right. Okay, notice that.
And so what you'll see is waveforms here all built up and spread apart on that side. So that was cute. Anyways, moving on here. All right, so with this one, we'll go back to the website here. I can actually make the plane go, say, half the speed of sound. So a Mach number of 0.5, half the speed of sound. Which doesn't matter, I don't have to get it exactly, right? And so what you end up with is exactly what we showed, the wavefront all built up in the front. So basically in between times when the wave is generated, the plane moves in the direction, sort of keeps up with the wave, closer to being keeping up the wave. So it compresses them together. And then from behind, they get spread apart. Okay? And the closer you are to the speed of sound, the tighter they are on the one side and the more spread they're out there on the other side. Okay? So that's just something you want to be able to understand and visualize. And so what we're getting is this pattern. And so I think we should be able to predict what the pitch would be heard as. If you think of this section here, the wavelength is compressed together. And so the frequency at which the waves go by your ear would be higher. And so it'd be heard as higher pitch. And these are going apart less frequently. So it would be lower pitch. Okay, so you're getting that answer there for higher pitch and lower pitch. So as the pitch heard reduces from the higher pitch to the lower frequency, it actually is going to pass through the actual frequency. So think about the actual frequency is producing of 2,000. This increased frequency here might be like 2010 or something, in which case this one's probably going to be 1,990, right? Just add 10 and minus 10 basically by the motion of the wave, okay? So we already showed this part, but when they're compressed together versus spread apart. So the nice thing here is we have a wave, a sound wave, right? Which we now believe and are justified to know it's actually a mechanical wave. And we have yet another physical wave, water waves, that you can show or behave the exact same way. Okay, so the model is good. Doppler effect.jar here. I need to go to Doppler jar. And so I'll get this program running. It might have already been going. But so there's a fire truck that's stationary. And if I move the truck, go back to normal here. If I make the truck have a velocity, then same deal, right? You get into the compression. That's actually a really fast velocity. So they're compressed super close together. Might be more normal to have, half the speed of sound or less, of course, right? The kind of speeds we travel at are a lot less than half even. Okay, so, but I do want it to be obvious. So like I want this to be obviously compressed on one side and spread out in the other. So that, yeah, we can adjust the speed and so on. If I go to the three-dimensional version, it's kind of nice because they show like the sound wave, the red, and then they have this like three-dimensional look to it. So if I go a good percentage here, you can see the sound wave they're showing is maybe a little too compressed here, but it's it's very tightly compressed there. Let me go to a different one here. That maybe. So you can see the typical sine wave and obviously shorter wavelength versus longer wavelength. So high frequency sound and low frequency sound. And again, with no speed at all, right? With no speed at all, the frequency that the truck's actually producing is in the middle of the high frequency and the low frequency. So that's something I want you to sort of think of as we look at some of these videos later on. I'll mention it again, of course. So here the waves are compressed together due to the motion of the sound source. And so you have a smaller wavelength and you hear high frequency. And here they're spreading apart. So it's longer wavelength and lower frequency heard. Okay, same deal for that. This was just an applet that used to work that showed the same kind of thing. All right, so let's go with these ones first here, actually. I'm ready to go. So there's what's called a Doppler rocket. I have one of these in person here. I was going to try and do a video, but I'd have to get a helper. That person has to finish writing their paper. I'd have to get a helper. So I found a video online that's the same as what I do. Go to that since they're looking for ad revenue here. So this little football-shaped thing with a hole through it can slide back and forth on a string. And so that tone you're going to hear, okay, you'll hear what that tone is when it's going towards and away. So here it goes, higher pitch and lower pitch, higher pitch and then lower pitch, right? So when it's going towards you, the wave fronts are compressed together, making it sound higher pitch than it actually is. And then when it's going away, it sounds lower than it actually is. What it actually is that pitch. Kind of fun to play with. So that is that version of it. And then the Doppler rocket circle is a little harder to visualize what's going on if I just show this, but it works to where the 202 mark here, he stops yapping, and here we go. So there's the sound it's making. So what you're hearing is the frequency going higher and lower as it's going towards you and away from you. Okay, so it's the Doppler effect. So those are good. This 2010 here, I'll just type in. And I need my video folder. So the actual frequency of the Dodge van horn.
Again.
So this is me out in the van on the road beside the school, and we're listening to the Doppler effect with a previous class that I taught in person. And so then this is the van going by. And so you'll actually hear a higher pitch. That's higher than what we just heard. If you have pitch memory going on, that's higher, and then it's going to transition through the actual frequency down to a lower frequency. And you don't have to be going very fast. I didn't have to like break any local speed limits or anything doing that at all. What's next here? Doppler effect car horn. There's lots of versions of this, but in my files here. Doppler effect. Same deal. So what you're hearing is higher than what the horn is producing. A little greater change there because of the higher speed. What did I have? The train horn is awesome. Train horn, Doppler, air horn. Probably right there. I'm just not seeing it, but there we go. Train horn, Doppler. So this is one of those things you can easily end up noticing in the world around you of the physics, what we're doing. So very big change, whipping along there. And so the sound like I said, it sweeps through the original frequency that was produced. Even the European fire trucks are good too. European truck somewhere here. Oof. So that one's kind of neat because you got these two distinct tones. And so it's going between two higher tones, and then it transfers through the actual, and then all the way down to two lower tones. So it's just definitely. I saw a video once of a band, like a high school band on a wagon and in a parade, and they're playing like Happy Birthday or something, I think it was, and then the tractor that was towing them went by, and it was interesting to hear like just the natural sounds of the high school band doing that same Doppler shift of all of the sounds that are just the saxophone and the flute and the clarinet and all those things. Motorcycle sound is interesting too. This sound is just around us everywhere, even with sounds like not without a horn. Motorcycle sound. So that kind of sound that something makes as it goes by. Right, that sound as it goes by. It is the Doppler effect as well. It's just all the sounds that the engine and the wind noise, all the sounds that are being emitted. Back to air horn. This is just people basically taking a little physics video on their own here. So air horn. So Ethan and his Doppler 1. There's the air horn. So that's nice. You hear the actual pitch, right? Just honk the horn. So remember that pitch. And then as he goes by, ready? Bar here. All right, very obvious Doppler shift going on there. All right, so it's just, like I said, nice physics phenomenon that's in the world all around us. Big Bang Theory, he dressed up as the Doppler effect and then describes the effect over and over again. I'm not going to play that one because I think it's probably more likely to be copyrighted. So this video is a little hard, like it's a little hard to follow, but basically if you watch this one long enough here and look at the parts here, they have a family that are making this Doppler effect video, and they have walkie-talkies. And so they try to get it so they can show you the sound the horn of the band's really making, and then the sound as it's going by, and so on, and try and show you that they're all the same. So if you have a chance, click on the link and it'll they do that. But car horn, it's worth trying to show here. Car horn, not in physics resources, that's why. In my video folder. Videos, car horn. It's pretty interesting the way they do this.
Okay, welcome to the Adler Scientific Society.
Doesn't seem creepy at all, does it? So let's keep going here.
So the funny thing is,
I'll just try and cut to the chase here. So you're hearing the sound of the horn there. And now you're hearing the higher pitch going to the lower pitch. And then eventually they have, is it there? So you can hear both at once there. You can hear the high one and the low and the medium one. And then the loudest one goes to the lower pitch. So hopefully you can hear what I'm trying to show there. That that the pitch that's actually producing is, of course, the actual frequency. You get this perceived change just by the motion of the source of the sound. So notice we talked before about how the frequency of a wave, once it's created, can't change. What's happening here is it's being heard as a different frequency. It's not actually a different frequency. It's being heard as a different frequency because of the motion. But absolutely, I've been harping on here that the higher pitch because of the shift, and we have the actual frequency, and then you get the lower one, and that shift is the Doppler shift. So some applications of this, it's used in radar and speed traps. So what happens is the radar goes out, picture the certain frequency that the waves are going out at. The object that's moving towards the police vehicle moves, and so picture there being a reflection off of, I'll just put an object in here to show. So picture the waves reflecting off of an object, right? And so this wave reflects, then the object moves towards as the next one's getting to it, and then it reflects. So the reflections come back compressed because the object is moving towards as the waves are bouncing off. Okay, so that's how radar works. That description shows what I just tried to show in person there in a step-by-step. But the frequency that is being sent out is a blue one. Because of the car's motion, the frequency, the red one, comes back as Doppler shifted. And then there's a measurement inside a sensor and a calculation that calculates what the speed of the vehicle must have been. Another one you might have heard about is Doppler radar, Doppler weather. So they send up sounds into the clouds. The movement of the environment, movement of the atmosphere, causes a Doppler shift in the reflected rays. So they can map out the motion of the atmosphere. A weird musical example is a speaker called a Leslie. I don't know why they call it a Leslie. I should look that up. But the Leslie is a sound that a rotating speaker makes. So Leslie 122 overview. Leslie 122 overview. There we go. So if you have a speaker that's rotating, it just makes a neat sound. And so it was a sound effect used in like the 70s. Right? It sounds like vibrato, sort of. So you can change the speed that it goes at, and it makes that kind of whirring sound up and down of the sound. So it's very similar to in a guitar vibrating the string, to make it sound interesting, or violinists do it all the time, and even singers do it as well. Singers do it just to kind of mimic what instruments do because it sounds good. Here's just a rotor speaker simulation in a program, right? And it's really just it is a simulation of that rotating speaker, and then so it makes that sound.
Turn on the LFO, center it, readjust the speed of the panning.
So that sound was originally made with literally a rotating speaker called a Leslie. But it's the Doppler effect, right? What do we have next here? So Doppler shift in astronomy. I don't know, the applet that I had going here has a star version, and it's not done super well here, but basically, depending on the speed, there's a shift, and so basically you see the frequencies of the observed light that's coming from the star shifts because of the Doppler effect, depending on the speed. So the faster the speed, the more it's shifted towards the blue end of the spectrum. But the way the applet was designed was a little bit hard to sort of see that, but that's the idea. So basically, if things are moving towards you, they shift towards the blue, and if they're moving away from you, they shift towards the red. Because from your grade 10 work, you probably remember, hopefully you saw, the red end of the spectrum is the long wavelength, and the blue end is the high energy, short wavelength, high frequency, short wavelength stuff. So it's really good information about the universe around us. Because if you look at the absorption spectrum, like this is chemistry work, right? This is in this gas cloud here. These are the bands of light that are being absorbed. And so if you look at that spectrum, you can tell, based on the sequence, you can say, oh, that's hydrogen, or it's neon, or whatever it is. And then if it's shifted from the normal positions, you can tell, oh, that galaxy is moving away. It's red shifted, so it's shifted towards the red, and this one's moving towards us. It's shifted towards the blue. Okay, it's very easy for spectral analysis to help identify how fast something is receding away from us. It's very easy because we know what the key, the pattern, the spacing will tell you what kind of element it is, and then how much it's shifted from what we see when we're at rest relative to it is very easy to identify. So what's found is that the farther away something is, the more it's shifted into the red, which shows that things are moving faster, moving away from us faster and faster, the further away they are. And that's actually direct evidence of the expansion of the universe itself. Okay, so the more space there is between Earth and the object, the more expansion there is. Like if you just had this much space, then it might expand this much. But this one would expand that much as well. And so what I have here is I have the green arrows, twice the size. So if you're twice as far away, then there's going to be twice as much expansion because each section expands by the same amount, right? So they call it like the raisin bun effect or whatever. Like if the space in raisin bread, the bread space between raisins, if each one grows by a centimeter, then two that are farther away are going to go 2 centimeters apart, right, rather than 1 centimeter apart. So just to help you understand the evidence, and how we know, and it's based on the Doppler effect. A lot of times people ask, like, how do they know that? And this is one of the ways. Video. This is just a silly joke that if you understand the physics of what we're doing, you understand that it's a joke, right? So Heisenberg driving gets pulled over by the police, and asked if he knew that he run a red light. And he said, no, I didn't see the light as red because it was blue shifted because as I was approaching it, right? The opposite effect of what we're talking about. And so the cop gave him a speeding ticket instead. Obviously, he must have been going really fast, right? So instead of getting a ticket for running a red light, he got a speeding ticket. The next thing we can talk about to do with motion and effect on sound is the idea of what happens if we're going faster than at the speed of sound or even faster. And so if you're going at the speed of sound, let's go to the program here. So I'm going to drag this till it's a 1. If I can nail it here. There we go. So if you're going at the speed of sound, then all of the energy that's put into the air and the sound waves that the thing has ever made, right? And certainly while it's moving, all that sound energy is building up in front of the object, and so that's what they call the sound barrier. And then if you go faster than the speed of sound, you actually end up ahead of that big pressure wave. And so it's actually easier to speed up and keep your speed going and accelerate if you're going faster than the speed of sound, because you would have broken through that pressure wave that builds up in front of you. So we have this sound barrier, like I was saying. So that's all of the sound, the energy, the pressure from the whole time since it started moving and making sound and so on. So that's basically constructive interference. All that energy is adding up. Use another word from the course. And so that high pressure is pushing against you. And so it's very hard to go faster. To break the sound barrier is difficult. If we're going faster than the speed of sound, then you end up ahead of that, right? So you end up ahead of this this area. There's high pressure and low pressure, and you're ahead of that. And then that sudden change in pressure can actually push and then pull on things, and it can break glass, it can break walls, it can do a lot of damage, can make people go deaf if it ruptures their eardrums. So yeah, since the plane doesn't have that high pressure against it, it can actually speed up. So if you have the jet engine on high power and you're just getting to the sound barrier, once you actually break the sound barrier, you actually feel yourself accelerate more. It's like you all of a sudden are free to speed up again or more. A weird thing. Some people have asked me too, like, so if you're going faster than the speed of sound and you're in a jet engine, or like if it happened to be a quiet enough airplane inside, could you talk to each other? And the answer is, well, yeah, because you're inside, there's air in there, right? So the sound waves are going to go through the air that's traveling along you at faster than the speed of sound, with you at faster than the speed of sound. But it'd be a different story if you had two planes flying side by side and they were to open the hatches and try to talk to each other. That's not going to work for many reasons, but one of them would be because the sound waves wouldn't be able to travel fast enough. There's a similar effect with boats. There's actually two sonic booms from boats. It's the bow wave and the stern wave. If you notice when you're driving across the lake in a boat, and there's the same with breaking the sound barrier as well. So the first airplane to break the sound barrier was the Bell X-1. I'll show you a little video about that. Oh boy. Bell X-1 supersonic plane.
In the 1940s, the U.S. began testing a series of experimental aircraft designated as X-planes. The Bell X-1 was designed to investigate flight beyond the speed of sound. Very little was known about the aerodynamics necessary for supersonic flight, so the X-1's fuselage was modeled after an object able to travel at this velocity, the .50 caliber bullet. On October 14, 1947, piloted by Air Force Captain Chuck Yeager, the X-1 became the first aircraft to break the sound barrier, Mach 1.06, 700 miles per hour.
So that's historical there. First one ever. There's a Canadian link, the Avro Aero. If you look into it, there was a Canadian project to build this really awesome airplane. It was actually state of the art, best. It would have been, really cool. I would have gone way faster than that. It got canceled, and there's a big controversy about it, all the money that was wasted, and should they have canceled or not, and so on. That simulation doesn't work anymore. So I'll show some sound barrier stuff. So sound barrier 2. This one has. So there's a weird effect in the air when sound barriers are being broken. And so the big pressure wave of high pressure and then low pressure actually creates condensation, comes out. And so you'll see cones. It's just a funny video here, but there's a bunch of people on an aircraft carrier like waiting for the shock wave to hit them. This is the aircraft carrier one. There's the aircraft carrier one. So they would hear this like intense bang sound, and so that you can see the shock wave trailing behind the plane there. And there'll be times where you can see a cone behind them in the air itself. There you go. There's a spot. So that just didn't pause quite in time there. There you go. So that cone behind them is that shock wave. And the push and pull is causing water molecules to like form into droplets. That's why you're seeing it. So you'll see it. It looks fake, to be honest. Like it's just, but it's not. It's just what happens when the water molecules come out of suspension or out of vapor form. Sonic boom, extreme close flyby. Flyby. So here's so what you'll hear there is you'll hear people cheering first. You don't even hear the airplane yet in actuality, right? And then you'll hear the kind of the boom, and then you'll hear the airplane. So you hear the airplane flying away after that shattering boom sound.
Got it.
So this is just pictures. So supersonic flight. I believe this one's just pictures. But pictures of that cone
That's
that you
about
see behind. Oh, there's one that's pictures. There you
So
go.
if there's enough, then there are the shock.
Yeah.
Shock can't get out of the way fast.
See the sound. See, actually, you can see in the air. It's
then
weird.
There are the shock.
This disturbance in the air is being picked up by that camera. It's really weird. Apparently, it causes refraction as well. These
into ideal conditions for showing.
I'll skip that one for now. There's a video I have of SpaceX rockets landing. I'll have to find it if I don't have it in the folder. I'm just thinking of it now. Here's the still pictures, but that's the kind of thing you see. They look super fake, but you know that picture there is that's just water droplets condensing out. Here it is here. SpaceX Falcon Heavy rocket. Wouldn't mind witnessing this. Oops, that's not the one. Everything is going on at once here, I think. There we go. So pretty cool. They're like way, far away from the landing site here, but there's these two Falcon Heavy rockets that are coming back down.
1 and 2.
And you can't hear them at all.
2 candles coming down. There they are.
And that's the shockwave. It's crazy. So you can hear the video going on. You can hear people talking. There's the sonic booms from the two rockets. They're coming in at faster than the speed of sound. So you can't hear them at all because their sound hasn't gotten to us yet.
Double sonic booms.
And then you can hear the rockets after that. That's pretty cool. Would be neat to witness for sure. Last little bit is to do with sonic boom and breaking glass and so on. So Mythbusters does a big episode on if sonic booms break glass and so on. I will try to show a tiny bit of it. Mythbusters sonic boom. Let's see if boom. Sonic boom sound off. Let me just go zipping ahead here. So they're basically getting the Blue Angels to bring to make sonic booms and see if they can break glass. And the myth was that sonic booms always break glass. A little bit too specific. More like I'm thinking it would make sense to see if it can break glass, which they show that it can eventually here. Excuse me. And so here's the plane going by, and there's the sonic boom. And then they go over and they look at the shed.
Before Jamie can get in and check the results, Ben blasts by. As per the myth.
Oh no!
So
it blew the window out of its hole, but it didn't break it.
So it actually knocked the window out of the hole. The high pressure broke the window free from its frame. It just fell down on the ground and didn't even break, which is hilarious. Eventually, they get low enough and hard enough enough energy that they get the glass to break. So right there, the sonic boom was enough that it breaks it.
200 feet.
Where is it?
That's what I'm getting. Well, it didn't break at 200 feet. I got to go check it out.
They might show a replay of it for me.
Nothing. Like the glassware. Good story.
There we go. The video is a little bit delayed on what I'm playing here. As I'm clicking.
Well, almost. But over at the house, it's a whole different story.
There we go. Sonic boom comes in. The pressure wave pushes so hard that it breaks. And that's what's going on. That high pressure and then low pressure. And then other applications. So what makes the sound of the lightning and the thunder? Like the thunder is actually air molecules. This is crazy, hard to believe. But it's air molecules that are heated so fast and they expand so fast. They expand out faster than the speed of sound and they make a sonic boom all the way along. That's what thunder is. So you can't understand what thunder is without understanding motion and sound effects and sonic booms. Also, a whip crack. The tip of the whip goes faster than the speed of sound and makes a cracking sound. So speed, sound speed, demo, no. Yeah, sound speed whip, I'll type. Probably can just type whip, to be honest. I don't have too many whip videos, I don't think. Whip crack, sonic boom, sound speed demo.
This is a demonstration of this.
So this guy knows how to crack a whip. That sound you get is
that heavier and
harsh cracking sound that that the world's loudest whip crack. That's whip crack. So that sound is
1, 2, 1 points.
Okay? That's a mini sonic boom. And that is it. That's everything that I have to show you to do with Doppler effect and sonic booms and so on. So hopefully that makes sense to you. And if you have any questions, let me know. I will get out of here for you. Talk to you later.